Welcome to video number 12 in the Fortitudo.tech Python package walkthrough. In this video we'll be going through the Python code for the normal distribution myth SSRN article. So as always, we start at the front page of the repository and then navigate to examples. And here you can see that example number 12, it's called normal distribution myth, and this is the one that we'll be going through today. So basically this Python code presents all the computations that have been performed in this SSRN article so that you can verify them on your own, and you can potentially change it with the data that is relevant to you. So let's just go to SSRN and see what's in this article. And here in the article you can just open it in your browser, and basically, as you see in the abstract, historically finance, economics, academics have made the assumption that returns follow normal distribution. So you can imagine something like CAPM, Black-Litterman, mean-variance. But for anyone with just some practical experience with investment management, it's quite obvious that this assumption does not hold. However, academics, they keep insisting on that on a longer horizon, then the return distribution should become more normal. And this is something that they call aggregational Gaussianity. So basically, this refers to a situation where you have log returns over a longer horizon, and then the longer horizon log return is just the sum of the shorter horizon returns. And then they argue that this should become more normal because it follows some central limit theorem. The problem is that they don't really define the central limit theorem, and when we perform a test for 10 US equity indices, as in this article, for normality on longer horizons using 26 years of data, well, then it seems that the assumptions that underlie this central limit theorem are not really there for real-world investment data, so that we reject this normal distribution assumption even on longer horizons. So this is also something that you can look into, and in the article there are also an explanation of some of the logical issues of using this aggregational Gaussianity argument to justify CAPM, Black-Litterman mean-variance, because of course on longer horizons the difference between log returns and discrete returns becomes larger, so the approximation becomes more poor. And when we do portfolio optimization, of course we want to have the discrete returns because these are the one that aggregates across positions. So yeah, this is something that you can read about in the article, and here in the introduction, I just present the things that I basically said to you here. And also some references to interesting case studies that also reject this aggregational Gaussianity hypothesis. And actually there are some studies that perform simulations where they know that the aggregational Gaussianity cannot exist, and just show that if you don't have enough data, then you can falsely fail to reject the normal distribution hypothesis. So basically this observation that we have had about aggregational Gaussianity, it's probably just related to a small sample size, which is inherent to longer horizon returns. So that's probably how this idea came about. And also the evidence for this aggregational Gaussianity has never been really strong. It's just usually argued in a vague way with a undefined central limit theorem, and then just some visual analysis where things seem to become closer to normal distribution, or some naive test where you just have kurtosis that become closer to 3 without looking at skewness and other elements of distributions. So here in the second section I present the logical arguments about using it to justify the old methods, and then we go to the case study where we have 10 US equity indices since December 22 in 1998, and basically it's just to maximize the number of indices that we have. So some of the new US equity indices that were introduced after they are not included, and basically this data is just as much as we could get from Yahoo Finance, and this is something that you can also download for free, so that's why we decided on this period. In total, it gives us 26 years of data and then 100 additional days. So what that means is that we can compute 25 yearly returns with this data with 100 different starting points. And with this 100 different starting points, of course, there is no reason for us to believe that some of them are more important than others. They should be equally important. But the point is that we get 100 p-values and test statistics for 3 different normal distribution tests. So this is this Shapiro-Wilk and this K-squared and Anderson-Darling test. This is the one that we use, and basically the way that we chose these is based on their small sample performance. So there also exist other normality tests that were with this understanding that they are more valid for larger sample sizes, but since we only have 25 for the yearly returns that we want to test, then yeah, we choose these 3 tests to compare it. If you run these tests on daily data, on monthly or quarterly data, well, it's very, very clear that the normal distribution assumption is rejected. You can verify it by looking at the code, and it's also even the finance academics, they do not argue that that it should be a normal distribution on shorter horizons. But here we also just show that even on longer horizons, it's not it's a dangerous assumption to make. All right, so here we just show you the p-value of this K-squared test for the S&P 500 index, and then similarly for the Shapiro-Wilk test, and then finally we show you some test statistics for this Anderson-Darling normality test. It's apparently hard to compute the p-value, so this is why we show the test statistic, and the critical value is this 0.705, so everything above that it rejects the normal distribution hypothesis. There are also some people that argue that index returns should become closer to a normal distribution because they aggregate across the individual instruments, but whenever we just perform some elementary analysis looking at the data, then it's very, very clear that it's not the case. So basically, the index return do not become normal, the longer horizon returns do not become normal, and for portfolio construction, risk management, if we are to use, let's say, mean variance, it's not just normality of one distribution, but it's a joint normality that we need, and constant and linear dependencies and things like this. This is something that you can read about in the portfolio construction risk management book, where I present all the details why there are so many issues with mean variance. Okay, and this is basically here in the final section where I give references to an investment framework that overcomes in a natural way all the limitations, or the main limitations at least, there are with the old methods based on the covariance matrix and the elliptical distributions and things like that. All right, so this was the walkthrough of the article. Let's go and then look into the code. First, we import the packages that we need. So Yahoo Finance for the data, the Fortune Tech package for analysis, and Matplotlib to show some illustrations. And then here you can see that from SciPy we can import the different tests for normality that we want. So here with Yahoo Finance we just download these US equity indices that we want, and then rename them so that the names are a bit more descriptive, show you how the data looks, and then we illustrate this fact that we have 26 years of data with 100 different starting points, and then we have here different horizons that we compute returns on. So here you can see that this is 1 day, 1 month, 1 quarter, and 1 year. So we make the the usual assumption that there are 252 trading days in a year. You can adjust this yourself if you want. And here we just show you the simulation moments of the daily log returns. And you can see that there's a lot of kurtosis, a lot of skewness. So even university academics do not argue that this is close to a normal distribution. And then we just perform some of these normality tests for the daily returns. And you can see that we have very, very low p-values for the Shapiro-Wilk, also very, very low. And you can see that this test is even that, you know, if you have more than 5,000 observations, then it becomes unreliable. But for the tests that really matter, we have significantly less than 5,000 observations, so that's fine. And then here, we compute this Anderson-Darling test, critical value, report the test statistics, and show you how it looks. All right. So after that, we allocate some space for the results for the different horizons that we want, and then we start basically using these normality test functionality from SciPy to test on the different horizons and loop over the 100 different starting points that we have, so that we get a distribution of p-values and test statistics. And here, we just show you how you can generate these plots that are given in the article, where we choose the last index. This is S&P 500, and the last horizon. So this is the yearly horizon. And then, we show you basically the figures that you saw in the article here. You can adjust it. You can change the index here. You can change the horizon, and then you can see all the results. There's also a high-level description of this article that you can find on Substack. So basically, by following this link, and it's called the normal distribution myth. And in the main picture for this article, you can see that we have these different tests where we loop over the different indices. So basically, I created this GIF that will show you for the different financials, industrial, the test statistics, and the p-values. So you should be able to get the same results if you adjust the code, and then you can see for yourself. The main point is that for all horizons below 1 year, it's very, very clear that we reject the normal distribution hypothesis. And then in most cases, when we test for these 10 US equity indices, we also reject the normal distribution hypothesis. So basically, when people they find evidence of aggregational Gaussianity, it's usually driven by some bias that they want to justify the old theories and methods that they have written many articles about. So you could choose one specific period, one specific index, and then just show this one particular test that shows what you want to. Of course, we want to avoid this in the case study that we have here, because we want it to be scientific and actually test for how reality is. All right. So here in the high-level article, you can see that there are some more descriptions about what happens, some other arguments. And then finally, you can see that there is a reference to this applied quantitative investment management course. So basically, this is the course that goes through all the elements of the portfolio construction and risk management book in a careful way. Where you can see how can we work with methods that avoid making these oversimplified assumptions that are made in the traditional finance and economics methods and theories. So I highly encourage you to also check that out, because here you can also ask me questions if you have any doubt, but you will learn how to perform fully general simulations, how to stress test them, and how to analyze them. All right. So this is the end of this video, and as always, if you want this open source code to run as fast as possible on your computer, I encourage you to give this GitHub repository a star, and then I hope to see you in the next video.